Right. Vapor pressure. So if you go by the literal meaning, vapor pressure will be what? Pressure exerted by vapor. So it's called vapor pressure. But see, if you take a liquid substance, conversion of liquid to the vapor state takes place at any temperature. Even solid substance also undergoes vaporization. So you may say it's called sublimation. Okay, all right. If the evaporation of the water does not take place, then how in the North Pole and South Pole, where the temperature is -70, how do you get cloud? Clouds are there. After that, there is snowfall because rain gets converted into snow. This evaporation takes place. Okay. So if you simply say that vapor pressure is the pressure exerted by vapor, scientifically it will not be correct. So when we can use the term vapor pressure, let us see. Suppose I have taken a beaker. This beaker, from beaker, what will happen? This will all evaporate and it will go to the atmosphere. It will escape. Gradually, you will find the water layer here is decreasing. So in that case, I cannot measure its pressure. To measure the pressure, what I have to do? Say I have taken a beaker and I have placed it in a airtight bell jar. Okay. Say this is the liquid. So after covering, what I'll do, I'll evacuate the air inside the bell and I shall connect it to a pressure. So initially, what will happen? See, it will be zero because there is no vapor. Pressure will be zero. Now, this liquid which is present there, what will happen? Gradually, it will come to vapor state. Okay. So as the time passes, more and more amount of the liquid will be converted into vapor. Vapor is nothing but the gaseous state of a liquid substance. The substances which exist normally in the liquid state at room temperature, when it goes to the gaseous state, we call them as vapor. Okay. So because of that, we do not call it water gas. We call it water vapor. But we call carbon dioxide gas because carbon dioxide does not exist in liquid state at room temperature. So this more and more amount this vapor will come, and this vapor, as you know, from the kinetic gas equation, this vapor molecule is nothing but the gaseous state only. So they are going to obey all the rules of the gas. They will move randomly in all different directions, and it will go and hit on the surface of the wall. When it goes and hits on the surface of the wall, then it builds up pressure. What will happen now? You will find gradually it is increasing. From zero, it has come, then it will be here. Okay? It will be like, but it's still on, go on increasing as the amount of the gas increases. But a time will come, it will reach its saturation. See here. When it reaches saturation, then if you feel enough is enough, no more liquid should be allowed to go to the vapor state. No, in nature you cannot do like that. It will still go on, but it has already reached its saturation. Now, why does it go? See here. As these particles are hitting the one, it is coming like this. It is going and hitting it, again it coming like this. See here. Because we know in kinetic gas equation, we know that gas molecules, they randomly move in all directions. In all directions they move. And they change their direction only when they collide with each other or they hit the wall. So when it goes, see, it collides and it comes back. When it comes to the liquid surface attracts it and converts it into liquid state. So in saturation, say, imagine there are 10,000 molecules. Out of 10,000 molecules, you imagine that 100 molecules are hitting the water surface. That is, per second, 100 molecules are getting converted into liquid. So from there, 100 molecules of water will be converted into water vapor. Okay, so this is called dynamic equilibrium. In dynamic equilibrium, both way traffic is there. It is not that it is going to stop. So at that time when it reaches dynamic equilibrium, you'll find there the pressure but the arrow is not moving, it has become constant. So that is called the vapor pressure. So what should you write is in its definition? We'll write it here. The vapor pressure of a liquid is the pressure exerted by the vapor of the liquid when it reaches when it attains dynamic equilibrium. Please remember that. It is not going to change. It may change if you heat it. Because if you heat it, then you force some molecules to go. Otherwise, at that temperature, this vapor pressure will never change. Because it reaches the dynamic equilibrium. It's totally saturated. Very popular question. See, this is solvent, pure solvent. Pure solvent. Okay, for our simplicity, we can write here water. Okay, and I have measured its vapor pressure. Any temperature. Okay, see, this is the one. This is the nanometer you have. Here say this is the pressure. And I have done another experiment. Okay. Say it is sugar solution. Sugar solution. All right. Or any solution that you want. Huh? You can put alcohol also, anything. Liquid also you can put, solid also you can put. Huh? Sugar solution. So what do you have now here? Sugar. So this one also at the same temperature we are measuring is vapor pressure. You'll find here. See here. This pressure is more than this. So what you can write? You don't write. What about observation? Vapor pressure of solution is less than your solvent. See, these are observation. You can also, of course, you can at home too, you cannot make this one. But if in future, if you do an experiment, you will find that vapor pressure of any solution in any solvent. For simplicity, you can take water. This is always less than the vapor pressure of the pure water. Pure water means what? Distilled water. Okay. Now, why it is like this? See, if this is liquid, okay, from there, what happens? This molecule on the top, first it goes to the atmosphere. Then 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 it goes to the atmosphere. Okay. So this is the way what you have now. You find these are the. That is, this is called evaporation. So due to evaporation, the liquid becomes now vapor. So these are the vapor. Right. So now assume that you can see the molecules. So I'm now looking like this. I'll try to look from the top. If I look from the top, what will happen? I'm looking from here. If I see this layer, so how this layer will look like? They are all water molecules. Yet to convert it into vapor. Here, these are the molecules. This one. So in that case, what will happen? This layer will now go out. Then the layer below will be exposed. That is what we can say now. That entire surface area of the liquid or pure solvent takes part in evaporation. Because here I did not add any. Okay, let me write it here solvent. So it is pure. And what is this? This is the surface of pure So what you can now say? That entire molecules of the, no, I'll not write a molecule. No, not to make it complicated. Entire surface area participate in evaporation. It is coming out. Say when it comes out, this is the molecule. All right. Now I made a solution. Solution is a homogeneous mixture. So you will find in each and every layer of the solution, you will have equal distribution of solid and solute and solid. Equal means I'm not saying 50-50. Whatever number of solute will be present in first layer, same number of solute will be present in the middle layer as the last. Okay. So if you think these are the solvent molecule and these are the solute, solvent, solute, solvent, solute, solvent, these are these. So now if I look from the top, how to look like? See, these are original one. What we have now here? It depends upon how much solute you added. Okay. See. So these are the, from top you will not go to see. So these are the solute. Who is supposed to evaporate? The liquid solvent. But yes, because here all the molecules present in the surface are liquid molecules, all of them take part in evaporation. See here, is the entire area is available for evaporation? Huh? See here, is the entire area is available for evaporation? See?
No, sir.
Where you do not have solute solvent molecules. Some solute molecules are also there. So these solute molecules do not evaporate. So the number of liquid molecule on the surface is less due to the presence of solute molecules. So the less number of vapor will now come. Okay. In this case, what is going to happen? You will have less number of vapor. Here you have more number of vapor because all the molecules can go to the vapor state. Here, along with the solvent molecules, solute molecules are also there. So from there, liquid cannot come. So as the liquid molecules are less vapor will be generated. And as the less vapor are generated, there will be less vapor pressure. So because of that, we find vapor pressure of the solution is less than your solvent. Could you understand? Huh? Understand or not?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. I think all of you have visited Watts Lake. Anyone who did not go to Watts Lake? Huh? All of you have gone to Watts Lake.
Yes, sir.
Okay. Now see, in Watts Lake, you'll find in the corner some places there like this. Now, I'm not going to the bigger body. Here, do you not find some lily plants are there? Have you seen? Huh? Lily plants you have seen or not? Hey, kuch to bolo. Water lily you have seen or not?
Yes, sir.
What is the color of the water lily in what lake? How does it look like? Yellow. Huh? What is the color of the lily that grows in what lake? Hmm? What about you? Are you colorblind? Hmm? That is, you did not see. Simply you are telling me like this. Without going to what lake also, from top also you can see. From the road also you can see the water lilies are there. Oh, see here. Suppose this is the portion takes part in evaporation. Is it not the leaf of the water lily floats on water? Does it not float? If you keep quiet, I will not teach. As simple as that. Okay. I'm not a grandfather telling you stories. Huh? The leaf of the water lily floats on the water. So when the water evaporates, water below the leaf will it evaporate?
No, sir.
No, sir.
No, sir.
So in that case, what will happen? In this case, you will find the evaporation process is slow. Please remember, during summer in plains, many places, the ponds get dried and it causes a lot of problem to the people of villages. So how to reduce the process of evaporation? You'll find for that they grow water lilies or lotus in their pond. So the rate of evaporation decreases because water below the leaf will not participate immediate evaporation. Okay. So now we have already seen that pure solvent entire area to participate in evaporation, but in case of solution, the surface of the solution also contains solute molecules. So in that case, entire surface cannot participate in the evaporation. So the rate of evaporation decreases, hence vapor pressure decreases. Vapor pressure of solution is less than the vapor pressure of your solvent. This is our statement and observation. But you have to explain now. What will write now? It is because in case of solution, the solute molecules occupy some space on the surface of the solution. And as a result, the entire surface of the solution cannot participate in evaporation. So it generates less vapor. Therefore, the vapor pressure of a solution is less than its pure solid.
Done, sir.
Okay. Good. Now we are going to discuss about the vapor pressure of solution. Suppose in a place, if the wind is more or air is more, in that case, do you not feel that storm is going to come? Hmm? Hello. You have no idea of storm. All right. This example, so you will not understand. Okay. See, do you have more pressure or less pressure at the beginning of exam? Suppose the exam is begin to, you have say 6 subjects are there, and exam is today is what, Thursday, na? Suppose exam is going to start from Monday. Okay, so do you have more pressure before the exam or less pressure?
More pressure.
More pressure. So one by one, when the paper is, the pressure remains constant or increases or decreases.
Increases.
Increase.
When suppose your exam has already started, and out of 6 subjects you have finished 2, 3, 4 like this. So in that case, your pressure increases or decreases?
Decrease.
Decrease.
Yes. So please remember, the vapor pressure of a liquid or solution is found to be directly proportional to the amount of the liquid that you have taken. If the amount of liquid is more, vapor pressure will be. And if the amount of liquid is less, the vapor pressure is less. All right? So that we are going to discuss now. So now we are going for liquid, liquid, solution. It is your solute is also liquid and the solvent is also liquid. So as both of them are liquid, see initially when I told you that if the solute molecule occupies the space in the surface, then the vapor pressure decreases. So there I did not mean I have added any liquid, because I told you, I have given you the example of sugar and water. Okay. So when you have taken a solution consisting of two liquids, you know liquids evaporate. So if the solvent is A and solute is B, both A and B is going to evaporate here. All right. So the total vapor pressure that you have measured, the total vapor pressure will be equal to the sum of A and B. Okay, sum of A and B. So in that case, the vapor pressure of A is a part of hole pressure. Vapor pressure of B is a part of the hole pressure. So the pressure due to solvent, we call it is partial pressure of the solution, and pressure due to solute, we'll call it partial pressure of the solution, because we have measured the pressure of the solution. We cannot, you see, in the solution, I cannot measure the pressure of A and B independently, because both of them are now evaporating. If the total pressure is P, so total pressure will be equal to the sum of the partial pressure of A, partial pressure of B. That in class 11, you have already studied Dalton's law of partial pressure. All right. Now I'll go for a very famous law. It's called Raoult's. Raoult's. Okay. What Raoult say? It says okay, I'll not write. I'll first take. So this is P. So P is equal to a PA plus PB. It is the PA is the pressure of this, and PB is the pressure of this. Okay. So here I'll write PA is the partial vapor pressure of solvent, and PV is the partial vapor pressure of solute. All right. So now we find total pressure of the solution. This is the solution. Okay. So we find the pressure of this is due to the solvent. That is the amount of solvent molecules present. Amount of solvent molecules we can express in two ways: as the mole of number of moles of A, or mole fraction of A. And this is the partial vapor pressure of B, depends upon the number of moles of B or partial or the mole fraction of B. So now I'll write Raoult's. No, I will not write. First I'll explain, then I'll tell you. So what do you find here? Here you find PA is proportional to chi. Don't write, because this is not being given in your book. PA equal to chi. What is chi A? Mole fraction of solvent. Then what should I write now here? PA, that we always we write like this: K into chi. All right. What is K? Is the proportionality constant. See, things that come from here, huh? You have to do it. Proportional to constant. But you can find out. How can you find it? Nothing. PA divided by chi A is equal to K. Okay. Now very interesting thing. When K is when the value of K is determined, it is found to be exactly the value of vapor pressure of pure component. Means what? See, before I make the solution, before I make the solution A and B, I mixed A and B. But before mixing, A was pure and B was pure. So if I determine the vapor pressure of A, then I'll get a value. Okay. Now, when we have put this theory, we have found this, whatever the K value I get is exactly equal to the vapor pressure of pure A. Somehow this is not being given in your book. They are simply given a statement. So this one is a dialogue between you and me. Now, what does it say? Raoul's. Raoult's law says for a solution of volatile liquids, the partial vapor pressure of each component means what? A and B. It is PA and PB. Of the solution is equal to the product of the vapor pressure of the pure component and its mole fraction. Don't write. See, what did I put? K is equal to what? Vapor pressure of the pure component. Therefore, what I can write here? That is PA is equal to PA0. Why do you put 0? There is no impurity. 0 impurity means pure component. Into what? Right. So, in your book, they have given finally this. So, if you have understood, put it in a bracket. Okay. So after that, we'll write this. So now write.
Done, sir.
Okay. So now I write. Let a solution be made by taking to volatile liquids. A solvent and B solvent. Containing S yeah, mole fraction. Okay, so I'll not now I'll write this one. Each of them have partial pressure of PA and okay. It is difficult to write in the book. All right. Then what to do right now? Then according to Raoul. So what we can write? What does it say? The partial vapor pressure of each component of the solution is equal to the product of the vapor pressure of the pure component and its mole fraction. So what we can write? PA equal to CA0 chi and PV0 to PV0. What is PA0? Where PA0 and PV0 are the vapor pressure of your pure A and
Done, sir.
okay. So now we'll try to calculate the vapor pressure of the entire solution. So this is next part. Vapor pressure of a solution containing two volatile okay. It is A solvent and B let PA and PB are the partial vapor pressure of components A and B. Okay. Now we'll write here. According to Dalton's law of partial pressure, the total vapor pressure of solution P is equal to the sum of partial pressures of both the that is what P is equal to PA plus so that you know. Now let me expand it. Or what I can write P is equal to PA 0 chi A and PV 0. Why? Because we know PA is equal to PA 0 chi A and PV is equal to PV 0 chi A. Just now we have learned. Now see. This contains two components. So now what you know? In a binary solution means two components. We know the mole fractions, sum of the mole fractions of all components equal to 1. In a binary solution, chi A plus chi B is equal to 1. Or this is that right here, this equation is 2 and this equation is 2. Or chi A is equal to 1 minus chi B. Substituting the value of chi A in equation 2, we get see what you get. This one I'll replace with this. P is equal to PA0 1 minus chi B plus PB0 or P is equal to, I expand it. This, or what I can write, if I take chi B common, so I can write here now PB0 minus PA0 chi B plus P. This is equation.
Done, sir.
Okay, now what are the observations we can see here? See, first of all, from this equation, what we know? If you want to find out the vapor pressure of the solution, if you know only one of the mole fraction, you can find it. See, here I've written chi A is equal to 1 minus chi B. You could have written chi B is equal to 1 minus chi A. So in that case, instead of chi B, chi A could have come. So the total vapor pressure of the solution containing two volatile liquids can be calculated or determined by knowing the mole fraction of only one. You need not know the mole fraction of both. Second, see here, vapor pressure of pure component is constant. It does not change. See here in this case, difference between two constant is also constant, and this is also constant. See, if I plot this on in a graph, how it will come? See, it will come in this form. Don't write. It will come in the form of y is equal to mx plus c. This is constant. This is constant. Have you seen this equation earlier? Hmm? Y
Yes,
is equal to
sir.
mx plus c. Now, what is this? Is equation of what?
Straight lines, sir.
Straight line. Correct. So these are the two observations we could find from this equation. Yes, if you really plot it in the graph paper, you will get a straight line. Okay. See, this is the interesting part of science. So we'll write now. There are two observations. I'll write. One. From equation 3, it is observed that by knowing the mole fraction of any component, here you have taken, I told you I told you that conventionally you consider A as solvent and B is solute. So here what I have taken? I have taken the mole fraction of solute. But you can take mole fraction of solvent also. Instead of that you write chi B equal to 1 minus chi. From equation 3, it is observed that by knowing the mole fraction of any component, any one of the components, total vapor pressure of the solution can be okay. And second is what? The equation P is equal to PV 0 minus PA chi B plus PA 0 represents the equation of a straight line. We'll write within bracket y is equal to mx plus c. Yes. Hey, you try to draw with the scale, huh? Don't draw like me, huh? Are you having a scale nearby? Oh, chi b is equal to 0. See, when there is no chi b, A is pure. Because of that, we write PA 0. And when there is no A, B is pure. Because of that, we write here vapor pressure of PB 0, pure component. Now, see here, very interesting. On vapor pressure of one of them is less, other is more. Please remember, a liquid boils only when the vapor pressure becomes equal to atmospheric pressure. How much atmospheric pressure? 760 millimeter of mercury. So a substance which is having higher vapor pressure means it boils early. A substance with low vapor pressure, it boils late, or it boils at higher temperature. Clear? Now see here, very interesting. You can proceed from this side, you can proceed from this side. Suppose you have taken a component with high boiling point and go on mixing a liquid with low boiling point. As you increase the as you go on increasing the concentration of B, you will find boiling point of the mixture will depress because the vapor pressure is increasing. And if you do the reverse one, if you put A into B, and if you go on increasing, the component of higher boiling liquid is increasing now. In that case, you will find that one is going to boil. If you have to boil it, you have to boil at high temperature. So these are the things I have shown you. Okay. Now I'll just take few more minutes. Let me finish it. Here we have taken the example of vapor pressure of a solution containing two volatile components. Suppose one of the component is not volatile. Say you have to the water, you have added sugar. Sugar is not volatile. If you add salt, salt is not volatile. Okay. So in that case, what is going to happen to the vapor pressure? Vapor pressure of a solution containing non-volatile solute. See, don't write. We have found P is equal to Pa0 chi A, this is solvent, and PV0 chi B, solute. If solute B is non-volatile, then what will happen? PV0 chi B, that is PV, partial pressure, equal to what? 0. Because it's not going to the vapor state. So there's no question on any partial vapor pressure. So what will happen? Vapor pressure of the entire solution will be due to the vapor pressure of the solvent. So what will write now here? A non-volatile solute does not contribute to the vapor pressure of the solution because it is 0. Therefore, the vapor pressure of the solution will be only due to the vapor pressure of solvent. So therefore, what we can write here? Therefore, what we can write? If P is equal to PA 0 chi. So this is a modified form of Raoult's law. So what you will say now? Raoult's law. The vapor pressure of a solution containing non-volatile solute will be equal to the product of vapor pressure of pure solvent and its mole fraction. So what do you find here? P will be equal to PA0 chi.